I would like first to introduce that we decided to have some lectures by UST professors. So we call that IAS Commons. Some of you maybe know, may not, that there's a Lunch for Science series given by UST professors at Central every now and then, like 4 or 5 lectures a year. And those lectures are sort of relatively low level, meaning it says easier for people in business to understand. And I attend a few of them, and I find it's very, very educational for me, because I know the professor for various reasons, sitting on committee otherwise, but I never know what they're doing. And then only by attending a lecture given in Central that I realized, wow, this is interesting. So I figured that many of us probably don't know the professors here, what they're doing. Maybe in your own group, you know, but people outside, even the same department, sometimes not so familiar. So we decided to start this IAS Commons lecture series at a level which people outside department, outside school will be able to understand. And especially, you get to see them walking down the concourse, and at least from now on, say, oh, I know what he's doing, So, and maybe you can even ask some questions. So today, that's the first one. We originally planned to start in the fall, but we say, hey, why wait, right? And our basic idea is really for a relatively small group of people using a seminar room, which will be appropriate so that people can maybe interact more freely. But then, of course, my staff said that, well, the chairs in the seminar rooms are not that comfortable, so we use here. And in case also the seminar room can sit only 50, and so maybe it's too crowded. So today, the first one is given by Professor Sheng, which all of you know. And I'm sure some of you don't know his work, so that's why today's lecture, we hope that he explained to us why what he's doing so interesting. Ping graduated from Caltech before me, before Tony, and then went on to Princeton to get his PhD. And after working in industry, he's back here, and he's the William Mong's professor of nanoscience, and he will explain one area of his research. I know he has many areas. So today he will explain only one area. So let's welcome Professor Sheng.
Wow. Thank you, Henry. In fact, last week, C.T. Chen asked me to give this talk, so I agreed. And as Henry said, this is one of the 3 areas that I work in. And in acoustics, in which it started in the late 90s. And so today, I'm going to tell you something that's the latest. And in fact, the publication will appear soon. So what I'm going to talk about is hybrid resonant acoustic metasurface. Now, sounds pretty technical, but it is really very simple. It's so simple that I hope I will not insult your intelligence. Okay, so, but before I start, let me acknowledge my collaborators. And it's the long-term collaborator, Professor Yan, and Dr. Ma, Xiao Ma, is he here? No, not here. Yang Ming, who is here. In fact, he just defended his thesis last week successfully. And Xiao Songwen. And so let me start by giving you some motivations. Okay. Now, in acoustics, we always want to make the low frequency noise go away. Now, we are in the 21st century, and still you have low frequency noise everywhere. So why is that? Well, it's because there are some physical laws making the low frequency noise very pernicious and difficult to dissipate. I want to make an analogy to radar reflection from airplanes. As we know, in the Second World War, radar was invented by the British and was used in top secret to warn of the German bombings. And why was this so effective? It was because airplanes, of course, are mostly made of metal, and microwaves reflect very well from the metals. Now, actually, when you think about it, metal has a huge imaginary part of the Dulles constant, means it is a very good absorber of electromagnetic waves. So why does it reflect so well? It is basically because there's an impedance mismatch. Namely, you cannot absorb something if the energy of the wave doesn't get into the metal in the first place. And that's exactly what happened for a microwave at the air-metal interface. It just turned back because of the mismatch of the impedances. And so now we turn to the low-frequency sound. Now, for low-frequency sound, not only impedance mismatch is a problem, but also the absorption constant is very low. And that's governed by a law called a linear response, because the linear response dictates that the dissipation is quadratic function of rates. And at a low frequency, you have small rates, and therefore intrinsically all materials have a weak absorption at the low frequencies. So you have a double whammy. So when you come to low frequencies, what do people use? They use something that's soft and large. And so that's part of the so-called anechoic chamber. And of course, that's not going to work everywhere. You cannot put this outside or something like that. Not only is it not aesthetic, but it won't last long because it's a soft material. There's another issue, and that is people like to convert one form of energy into another. And one form is to convert acoustic energy into electricity. Now that problem has been around for a long, long time. Now, there's not much energy in acoustic sound. So let me be clear from the start. But nevertheless, if you can do that efficiently, there are quite a few niche applications that you can do in converting acoustic energy into electricity. And I will mention some of them later. So without further ado, let me introduce to you the concrete realization of so-called hybrid resonant cell. And in this particular case, the concept is applied to acoustics. So the whole thing is extremely simple. So it consists of a latex rubber film, 200 microns thick, okay? That's used for making a surgeon's glove, and is tightly stretched over a cell. The diameter A here is like 45 millimeters. And on top of that, you place a button. It's very light, 0.8 grams. The radius of that is like 20 millimeters. And then below here, you have a very thin cell, 17 millimeters thick. And you seal some gas in it. And here we use SF6 gas, but it can be air. Okay? We use that because it has the smallest adiabatic index. So if we use air, the thickness here is like 30% thicker, but it doesn't matter. So now let me explain what we mean by the hybrid resonance. This membrane, you might wonder, why do we put a button in the center? The function of the button is to introduce two low-frequency resonances for this so-called decorated membrane, DMR. One, the lowest frequency mode is at about 115 hertz. One, the higher frequency mode is at 888 hertz. So you will see the resonant profile later. But so you have these two resonances. Hybridize means you want to combine them in some way. And how do you hybridize these two resonances? Well, by introducing a spacing behind it with some CO gas. The reason is that this gives this decorated membrane some additional impedance. I mentioned before about the impedance. And you will see with this additional CO gas thin chamber cell, two resonances hybridizes into a hybrid resonance. And this resonance has the frequency that is in between the two original resonances. Now, what's the advantage of having a hybrid resonance? Well, the advantage of hybrid resonance is that in the original resonant mode, like the first mode and the second mode, they are eigenfunctions mathematically, eigenfunctions of the system, of this membrane, okay? And you cannot change that. It's fixed by the boundary conditions and the geometry, everything. And, but with the hybrid resonance, you have two modes combined into one, and you intrinsically will have 2 degrees of freedom. And you will see that 2 degrees of freedom can be used very appropriately. One, to match the impedance of air. Another one, to absorb the energy. So that's the advantage of a hybrid resonance, because it originates from 2 resonant modes originally and into one, and you will see the manifestation of this 2 degree of freedom later. So let me show you. The first function of this is that this is a unit cell, okay? And when you have a surface full of these cells, then you have a so-called a metasurface, because each cell is hybrid resonant. And each unit cell serves as a point acoustic sink at a particular frequency. Now, in fact, when I showed this work to Matthias Fink, who works on time-reversed acoustics, and he was very excited because he said this is exactly the time reverse of a point source, because the dimension of this is very small compared to the wavelengths. You will see the wavelengths is 152 hertz, which is like 2.3 meters, the wavelengths. So it's very small. So essentially it's a point sink. And when you have a time-reversed source, which is a point sink, it can be very useful in enhancing the resolution. Because without that, the wave come back to a point and then it bounce back. So you require a sink so that they don't appear again. Okay, so that's what I'm talking about. So if you put such a unit cell and you measure it, this is the frequency I told you about 115 hertz. The second mode is very high, 888 hertz is off the scale. And then you can see at 152 hertz, and you have 99.4% absorption. It totally disappears. It's because at this frequency, this cell completely matches the impedance of air. And then all the energy goes in and nothing comes out. So it's, and we call this the anti-resonance. So what is this anti-resonance? So let me explain this to you. And it's actually very simple. But so let me show you the two resonances that I told you about before. This is the first mode at the 115 hertz. And this is the normal displacement of the membrane. You can see the button here, which is rigid, so it looks flat. And this displacement is under an incident wave about 80 dB sound. So it's very loud sound, except when you measure it, it's an impedance tube, so it will not bother people. But it's 80 dB, so it's, so the displacement of something like 2 microns is very large displacement, okay? And this is the first mode. Now, this is the second mode, which is at 888. And you can see the button moves only a little bit, and the rubber membrane, on the other hand, moves a lot. Okay, so you can see that. Now, suppose you are at the frequency in between these two resonant frequencies. Okay, so then what happens? Then, from Physics 101, you will be able to excite both resonances simultaneously. So the result is at a particular frequency, which we called anti-resonant frequency, omega tilde. At this frequency, what happens is that the normal displacement, if you average over the whole surface of the membrane, is exactly 0. It's 0. And at this anti-resonant frequency, when the average displacement is 0, then I will show you immediately that it implies that this membrane, this decorated membrane, is totally decoupled from the radiation modes, which in this case is essentially the reflection and the transmission modes. And in this case, all the wave comes in and totally got reflected. And we have verified that a long time ago, and we have published many papers on this. So it becomes a very effective sound reflector, even though the membrane is extremely soft. So let me explain a little bit why this is the case. And it requires a little bit of physics, but only a little bit. So this is the normal displacement of the decorated membrane. Is a function of the transverse coordinate on the membrane, x. You can call this really x and y, the 2 dimensions. And we can decompose this normal displacement into 2 components. And these 2 components essentially display the degree of freedom you will see in this particular hybrid resonance case inherited from the 2 original resonances. And they can be separately tunable. So that's the advantage. Okay? So I talk about the degree of freedom. So one is the area averaged normal displacement. That is like a piston-like motion, up and down. Okay? And the other component is whatever that's left over. Okay? So we call the delta component. And so we decompose this into 2 components. So that's very simple. And now we show that there is, for the acoustic wave in air, there is something called the dispersion relation, which comes out of the wave equation, in which the spatial periodicity, which is characterized by a wave vector k, is always related to the time periodicity, which is characterized by the frequency omega. And this is omega divided by v squared. And this k, since this is a vector, you can have two components. One is parallel to the membrane, another is perpendicular to the membrane. So the total K square is these two terms. Now, on the surface, when you look at this expression, you expect all three terms, 1, 2, 3, to be positive, but not necessarily so. In fact, you can have this component to be bigger than that, and that will force the K perpendicular square to be negative. So you say, how can they be negative? Well, if K perpendicular is purely imaginary, then its square is negative. And in fact, we do have such modes, and they are called evanescent modes. Okay? They are not propagating. They don't radiate. Okay? So what we are going to show is that this component of the movement, in fact, couples only to the evanescent mode. And the reason for this is precisely because this component have the K parallel, which is larger than the right-hand side. And how can we know? Because this is whatever that's left over. And we know this K parallel is the Fourier component parallel to the membrane. And we can do a Fourier transform in 2D, and that will give us the real space profile of this. And since this component occurs only within the confine of the membrane, whose diameter is much, much smaller than the wavelength, and therefore its K parallel component must be have a peak at a position greater than 2 pi over d, where d is the diameter of the membrane. And the d is much less than the wavelength, and therefore this component is always much larger on the right-hand side. So what that means is that this component can only be coupled to the evanescent mode, and therefore it is essentially what we call deaf modes. Deaf modes. Okay, they don't reflect or transmit. On the other hand, if you look at the piston-like component, and you look at its K parallel component, you will see that it must have something looks like this. It's peak at 0 because it's flat, right? It's a constant, and therefore this component will be coupled to the reflection and the transmission. And when this component is exactly 0, like what I've shown you before at the anti-resonance, then the whole system becomes decoupled to the radiation modes, namely the transmission. And so the whole thing is reflected. It becomes decoupled, okay? So that's the explanation. And as I said, once you have a hybrid resonance, these two components becomes independently tunable in a sense, because it inherits the 2 degrees of freedom from the two original resonances. And we will see that serves a very useful function. Okay, so delta W is deaf, okay? Now, another thing is that we go back to the original thing that at 152 hertz, we have a absorption peak. And this is the decorated membrane by itself without the gas cell behind it. So, and then this is at the anti-resonance frequency. So you can see the profile is very similar, almost the same. And the reason is because, as I've shown you before, the absorption peak frequency, 152 hertz, is very close, but slightly below the anti-resonant frequency. So the profile is almost the same. But now, look at the vertical axis, the scale on the vertical axis. The scale here is 40 microns. Wow. Here is 0.2 microns. So it's 200 times. Now, let me tell you how we do this. In fact, this is measured by a laser vibrometer. Those are experimental data, okay? Those are experimental data. Those are experimental data measured by laser vibrometer, which can measure sort of a fraction of a micron very easily. The measurement was based on a Doppler effect. So these are also measured data. So you can see this very, very high compared with the anti-resonance. The profile is almost the same. So you can ask, what happened? What happened? Well, what happened is over here, the anti-resonance is a condition. It's not a mode. But when you put a sealed gas cell behind the membrane, you hybridize two modes at the frequency close to the anti-resonance frequency, slightly below it, and it becomes a true resonance, a true mode. And the maximum displacement becomes extremely high. And then it is because of this maximum, extremely large maximum displacement that it can do two things. Number one is that it can impedance match to the background. And number two is high energy density for effective dissipation. Now here, let me tell you already that you say, wow, this is so big. But you can see there is a component here that's a negative, right? Below here is negative. So the average displacement, area average displacement is actually very small. Only something like 2 microns, 2.5 microns. In fact, it is completely matched to the sound amplitude in air. So the average of this actually is very small. But the high energy density comes from a delta component, which is depth. And you have very high density. And it's fortunate it's depth, because otherwise, if you have 40 microns resonance and it can couple to the sound, then all our eardrum will be pierced by such loud sound. It will be impossible to listen to such loud sound. So fortunately, it is completely deaf. And therefore, it just dissipates the energy. And now you can see that these two functions, these two components, can be tuned independently. And so let me tell you a little bit about the mathematics, because what I'm telling you sounds like very heuristic, but actually they can be completely backed up by rigorous mathematics. Now, because we are dealing with average component, we are dealing with the radiation modes. Therefore, the system after area average, what's left over is just 1D. So the whole thing becomes a 1D system. And in 1D, the impedance is just the inverse of the green function. So I'm just going to tell you this without any justification because this is not intended to be a lecture course. But if you can accept this, that the Green's function for the decorated membrane, in this case, the impedance, which is defined to be essentially in this way, okay? And the CO gas, on the other hand, will have an impedance like this, and the two pieces are back to back, and therefore they are in series, just like a resistor. So you add these two components, and here I want to say that this green function, on the other hand, can be completely calculated. And I want to call your attention to the fact there is a beta, which is very small for the membrane. Membrane is not very dissipative, okay? So it is actually very surprising that it can totally absorb the sound energy, even though the absorption coefficient is extremely small. So these are the eigenmodes expansion of the green function. So I'm just not going to go into it. But if we limit ourselves to be close to the anti-resonance frequency, then this can be expanded, and this is a small parameter. So now we add these two, and we obtain the total impedance of this cell, this metasurface cell. And this total impedance will also have a relation with the green function of the whole system, and which is an inverse relationship, as I said before, because still 1D. And then in physics, if you want to determine whether there is a resonant mode, you look at the imaginary part of the green function. And if the imaginary part of the green function has a peak, then that tells you there is a mode. So what you want to do is look at the total system green function and look whether the imaginary part of that has a peak. And it turns out it's very easy to show that indeed you can have a peak in the imaginary part of the green function provided the imaginary part of the total impedance is 0. Okay? So that becomes a condition. And when this reaches a peak, you have a hybrid resonance, essentially. So essentially, the hybrid resonance is realized by adding another impedance at the back of the two original resonance of the decorator membrane. And now, how about the real part of the impedance? The real part of impedance has to be matched with that of the air in order to have total impedance matching. And therefore, the absorption is this. And you want the reflection to be 0, so that absorption can be 1. So you want this to be real part of the impedance normalized to the air impedance has to be 1. So this is the condition of the hybrid resonance. And you have two conditions, okay? And you can ask yourself whether there are enough parameters to satisfy these two conditions. And indeed, there are. So let me just show you that it's very robust because we can have two parameters shown here in red. One is the cell, gas cell thickness. In our case, in this case, is 17 millimeters. And another one is the anti-resonance frequency, which you can adjust by the weight of the button, for example. So it's fairly simple. And therefore, you can have two parameters to adjust to satisfy the two conditions. So it's very robust. Okay. So the beta is small. Okay. So it doesn't matter. So you have a new resonance state. And to account for the extra impedance of the confined gas, and you have the superposition of the neighboring eigenfunctions, and the gas layer undergoes adiabatic compression. By the way, when you see a gas layer behind a membrane, the picture of a drum naturally comes to mind. Okay, but this is not a drum. Okay, because in order to have a drum, the depth needs to be on the order of at least between 1/5 and 1/4 of a wavelength, something like that. And here is 2 orders of magnitude smaller, so it cannot be a drum. It's purely for the purpose of providing some additional impedance. Okay, and in fact, if we go to much higher frequency, we can see the drum resonances. Okay, so if you want to have a drum resonance, of course, they are there. Okay, so. So here is again, so we have summarized, we have two components. The average component, which is piston-like, can be used to match the impedance. And when you have impedance match with the air, what happens is that this average component is almost exactly the same in amplitude. as the incident acoustic wave amplitude, so that the incident wave feels almost there's nothing there. So it's impedance matched. The variance component, this is the variance component. Okay, this we define the delta every square. To take the average, you take the square root. This is the variance component. And this is, as I said before, this is depth. Okay, because couples only two evanescent waves. And these two are separately tunable, and therefore is very robust. One impedance matches, another one absorbs all the energy. So that's very useful. So here again, you can see is over 40 microns, extremely large. And here is the average component as a function of frequency. As you can see, at the maximum is only slightly more than 2.5 microns. So there's order of magnitude difference between the variance and the average. So 1 Pascal incident intensity is about 94 dB. So it's a very loud sound. Okay, so impedance match, and the variance is much larger than this average displacement. So the vibrational energy is localized, and you have high energy density, and everything is absorbed. So now you say, aha, this explains why you have total absorption. And in fact, we can show you this theory almost exactly matches the experiment. Okay, so, and we can have like 3 cells in which the button's weight is slightly different for each of the 3 cells, and the gas cell thickness is also slightly different, and then they absorb at different frequencies. So in the future, you can imagine if these things can be adjusted somewhat automatically, like by some kind of means, then this can be smart. You know, it can sense the incoming wave frequency and then adjust itself, and suddenly it becomes totally absorbed. Okay? And when you have 3 things in parallel, so you have an incoming wave come here, and it will seize the 3 cells in parallel. And so in order to predict its behavior, it's extremely simple. If you just have 3 impedances in parallel. So it just impedance inverse, you add them, and the total impedance inverse is a sum of the individual impedance inverses together. So you add them together, and you can explain all the absorptions. Okay? And one thing that's interesting is because this is a hybrid resonance, is a resonant mode, so the density of state is very high. What does that mean? The density of state is high is that this cell can absorb, totally absorb the energy of the acoustic wave over a cross-section that's 9 times its own geometric cross-section. So you can see that this is the Poynting vector, the energy flow. So you can see it just flow into like the sink. So this is really correct to say that this is something like a sink. Just flow into it. So in comparison, this is what we have. I've shown you this before. And this is what you call the anechoic chamber, and in which people do acoustic experiments. Of course, this comparison is somewhat unfair because the anechoic chamber is broadband, whereas we have a narrow band here. It's enormous with thickness on the order of the wavelengths, and they usually cannot achieve perfect matching. And by the way, the reason they have this conic shape is because of introducing impedance there is a gradient in the impedance. So essentially, you want to match the impedance with air, so you try to trick the wave into thinking that the impedance doesn't vary because it varies slowly, okay, over a distance. That's why the conic shape. And you can see it's a conic shape over here. And this is a human being. You can see how large these structures are. We can also make our resonant absorber slightly broader band than just a single frequency. So we can use many asymmetric buttons and put them on top. And then you can see there are groups of very high absorption peaks. And we can stagger this kind of cells and to fill in these gaps. And you can get somewhat broadband. And by the way, here is the thickness only 1 centimeter. So you can have, a few of these things, and you fill them up, and they become pretty broadband. Okay, not completely broadband, but fairly broadband. Now, another use is that when we have something that with huge amplitude, like 40-some microns, it can be used to some advantage. Okay, and the one way to use this is to convert this kind of kinetic energy into electricity. So this is easy to do. And so after some try, Dr. Ma, we call Xiao Ma, and has managed to use neodymium magnets and sort of attach some kind of wire, electrical wire, magnet wire, to the button. So when the button oscillates, it just pulls the wires up and down, and these wires are located between these neodymium magnets. These neodymium magnets provide something like 0.8 Tesla, pretty strong. Nowadays, this kind of magnets are pretty strong, and so when they move in a magnetic field by Faraday's law, they generate EMF. So it's extremely simple. So we call this the inverse speaker design. In a usual speaker, you convert the electrical energy into sound, right? And here's the inverse. Okay, so it's extremely simple. And right away, we already get efficiency of 23%. Now this is very high because people used to convert acoustic energy into electricity by using piezoelectricity, and usually the efficiency is on the few percent range. So this is very high, and we can do better. In fact, we are confident if we use more magnets around the ring or something, probably 40% is not a problem. So the potential applications. Now, what I'm telling you today is just acoustic applications. But the concept of hybrid resonance is very broad. Okay, it does not have to be just acoustic application. You can have many other potential applications. Okay, you can have many other types of resonances. And you just hybridize them by some means. In here, we use a gas cell to hybridize them. But for other resonances, you can use other means to hybridize resonances. And then they will have new properties, okay, just like here. And maybe they can be used to advantage. And it's very low cost, as I said. It's, no high tech. It's low tech. It's a noise management. Now it's narrow band, so a single frequency. But for example, we ride airplanes, right? In the airplane, we always have the 300 hertz hum, and people sometimes bring with them the bowls, the earphones, and you turn it on, you can have a sort of active suppression of this airplane hum. Now, that is a perfect application for our things because it's a single frequency, okay? And in fact, there are many low frequency noise which are generated by machines. And when they are generated by machines, they usually have a particular frequency. And those frequencies are pretty sharply peaked. And these things present a very good opportunity to be perfectly absorbed. And because it can be converted into electricity, they can have some applications. One professor told me this can be maybe put in some kind of sensor device because a lot of sensors use very little power. And therefore, some sensors are put on top of some kind of bridge or some structure that's very hard to be accessed. So if you use battery, you want to change the battery, it becomes a problem. The battery itself is very cheap, but to get a guy up there and try to change the battery, it becomes a really, really expensive task. So if you can use something like this, you can scavenging some energy from the vibration, which is everywhere, and then use that energy to power the sensor. Okay, that's good. Okay, so and it's also very green, and it has very narrow width, so it can be used to advantage as a filter. Okay, as a frequency filter, and it's, as I said before, it's an acoustic sink, and it also because it can amplify. Because it can absorb over like 9 times its geometric cross-section, it can amplify the signal. So it can convert into electricity, and electrical signals are very much easier to measure, believe me. So if you can convert that, and you can have a single frequency, for example, Malaysian airline, 370, 37.5 kilohertz, right? That's single frequency, right? So you can sort of weak sound detection. In the future, you can use this to detect a very weak sound, as I said here. So there are some niche applications, and so just summary is a very robust mechanism, and it can perfect match impedance and total absorption, and you can convert the total absorbed energy into electricity, and it's extremely sub-wavelength and also thin. And therefore, it might promise some uses. And the concept also may have other applications in other contexts besides the acoustics. So I'm just going to stop here. It's I spoke longer than I need to, but I'll be happy to entertain any questions we have, or we can discuss over coffee and dessert. Yes, please.
I wonder how do you come out of the idea that such kind of structure, the impedance of such kind of structure can match the impedance of the air? How do you come out of the idea? How do you think out of such kind of structure?
Well, that's a slightly long history. Okay, that's because in the past we have worked on the membrane resonators. Okay, and membrane resonators, and then we have a coupled membrane resonators, and then we discover you can have a negative mass and you can have a negative modulus and so on. So after that, I thought with all these positive and negative parameters, impedance match must occur, because we have so much freedom to adjust. So in fact, I remember it's 1.5 years ago, this is the IAS. So we have a program led by C.T. Chen, okay, on the metamaterials. And at that time, I pulled Xiaoma from the audience and told him, we have to do this. Xiaoma wasn't convinced. But later on, with Yang Ming's simulation showing the result, we got better results, and finally it got realized. So in the beginning, we are not so clear. I was not so clear. But I had a confidence that somehow with such kind of material parameters, impedance matching would definitely be possible.
Yeah. So at the beginning, when you researched about the resonator, the resonator only consists of membrane and button. Do the resonator also consist of the gas, or the gas you just add afterward?
Afterwards.
How can you come up with the idea to add some air to tune the impedance?
Tune the impedance?
Yes.
Because we observed that before, that when you have a resonator, and when we put some kind of hard wall behind it, it changes the characteristics. And I knew that when you put something behind it, it was the impedance that's playing the most important role.
And why, when you add the unit cell to three unit cells, how do this structure change the eigenfrequency? Because I don't see any couple between these three unit cells.
No.
They're separate with each other, but how can this tune the eigenfrequency?
They don't tune each other, no. They just exist separately because the frequency are separated. If you want the frequencies to be close together, then they can affect each other. So it's not the geometric separation. How are they? Well, right now they don't, but if the resonant frequencies of two resonators are close together, then they can affect each other, and this can be predicted by the simple, because if the frequency is similar, then they can the effect can be predicted by the inverse of the impedance, the summing. This formula is not approximate. It's pretty exact.
I just don't understand why, because they are separate, but how can they interact with each other?
Because once you have the wave in air, okay, then they are all together.
So so they interact with each other through the vibration of the air?
Of course.
Okay.
Of course.
Okay, one more question. What's the acoustic energy? What's the difference between acoustic energy and mechanical energy? Because acoustic energy is also the vibration of molecules. So I think it's also a kind of mechanical energy. And you mentioned that the acoustic energy changed the acoustic energy to the electric energy. You also you also accomplished this by changing mechanical energy to electricity energy, but not directly from acoustic energy to the electric energy. So
This is.
first of all, I don't understand the difference between the acoustic energy and the mechanical energy.
Mechanical energy can have vibration, right?
Yes, but acoustic energy is also a kind of vibration of the molecule, right? The vibration of the air molecule.
Yeah, I mean, but you know, you can have vibration at the interfaces. So You can say that's terminology, but the vibration is probably much more general. Sound is a special kind of vibration in air.
Yeah, I just wondering, are there any some more physics other than the Faraday law? Because you can just explain this all by Faraday law, but are there any more physics? Are there any special in acoustic energy?
Any special with acoustic energy?
Yeah, yeah. When you consider about acoustic energy, what kind of what aspects will you consider other than the vibration of molecule? I think it's
over here. We don't consider the vibration of molecules. We just consider just the amplitude of sound. It's a totally classical way of describing the sound.
Vibration of molecule frequency is much higher.
Yeah. Over here is
It's compression.
yeah, it's compression.
Rarefication,
It's rarefication and compression. It's not the vibration of molecules. Yeah, Mike.
Is it directional?
Pardon?
Is there any directional?
Yeah, good question. Yes. In fact, there's almost no direction. You can have oblique incidence. The reason is simple to explain because it's so sub-wavelengths. So its K-dependence essentially is flat. If you have a point source, of course, its K-dependence is flat. When you have an array of them, of course, if they are periodic, you might, but if they are all absorbed, then they might not. Yeah.
You say this conversion to the electricity is something 20%.
Yeah.
And some people like Mong they use a piezo electric.
Yeah.
Get a few percent. How about using your technique combined with the piezo electric?
Yeah.
The higher you somehow integrate this.
Yeah, piezoelectricity use piezoelectric material, but the piezoelectric material is basically insulators. So they can have extremely high voltage, but no current. So the current is extremely small. But there is some limitation. So maybe, yes, maybe if we use some very thin a piezoelectric film or something like that. But then it will produce a huge voltage. But due to its huge internal resistance, the current is small because the insulator.
Okay, let's thank Ping again.